All right.
Is in a box right now, right?
Well, yes. This is actually the manuscript. I am now, if you ever are curious about the process of going through writing a book and the different stages you have to go through, I'm getting schooled in that process right now because I'm going through the copy edit. I just got the copy edits, and so this weekend while I was watching a certain football team, between plays is actually a really good time to go through and copy edit your book. And so I got all those comments back, and I'm supposed to get them back to them by Wednesday. And at the end of the day, we're supposed to have the book published by March 1st. So it's at Oxford University Press right now, and we're working on getting it presentable. And so it is interesting because you do work with a lot of people. You work with the copy editor, you work with an acquisitions editor. There's a whole new world, and it's totally different from writing journal articles. Although the only way that I was able to write a book in the first place is you have to take it bit by bit, so I just looked at it as I'm writing 12 journal articles on these topics, and I separate it out and write each one. And that's the way you've got to do it. So, you can do it. Actually, if you can write 12 papers, technically you could write a book, so, it could happen. So the thing is, once it's out, so now it's going to be published by Oxford University Press, but it's not a book for just chemists. It's supposed to be a book that explains chemistry to people who haven't had chemistry in a while. So what I'm going to do is I'm going to talk a little bit about the book. I'm going to tell you a bit about my reason for it. There actually is a faith element to the book, but it is not on the surface. It is underneath. And so I'm going to explain a little bit by what I mean about that. There's also an art element to the book. Okay, Gayla Bent, I'm not sure if any of you have had classes from Gayla or from her husband Zach. They both have taught here at SPU in the past. Gayla's now at Cornish. And Zach is still here, so you may have had classes from them. She is a real, honest-to-goodness artist, and she drew the artistic-looking things. And actually, Mary Anderson is a student who graduated 2 years ago, and she did graphs for biochemistry, right, in lab class. And then I needed someone to do graphs for the book. And so I'm like, you know how to use Adobe, and you've done graphs, so could you please help? And I'll pay you. So that's how I got 2 illustrators / artists to work with me on this book. And they have different styles, but they produced all these different illustrations to help describe the main thesis. Of course, the subtitle is really important, How the Periodic Table Shaped Life. So this really is about chemistry. Now, I didn't include chemistry in the title because that might remind people of a bad experience in high school. But everybody loves the periodic table, right? You know, we have, like Breaking Bad, they put all the little letters in the periodic table. So I didn't want to do that exactly, but I wanted to allude to it. Okay? So this is the actual cover that they've designed. And it includes, there's actually a secret message behind the elements that were chosen here. They took a big hand in designing the cover, but you can see that I don't have a really high resolution image yet, but I did pull this off of Amazon. It's also up on the OUP, Oxford University Press website. So where's it going to be? You know, it's actually going to be on the popular science shelf. So if we can get it into Barnes & Noble, which is no sure thing in itself, but if it gets in there, the idea is that it would be on this popular science shelf. They're arranged alphabetically. It'd be right next to paranormal romance on one side, and I'm not sure what else on the other side. Okay, but the idea is hopefully somebody would walk along and see the cover and think, oh, dolphins and chemistry. I wonder how those things go together. And then they'd pick it up. The idea of the title is to convey a couple things about the book. It's supposed to be like, you may have heard of big history. When people talk about big history, they're talking about usually human history. You know, I guess they're using history in its original term. But I want to think of this as a big natural history book. There's a lot of things in which ways in which I think chemistry helps clarify some of the stages that life went through. And I think that things look a little different when you look at natural history as a chemist than you do if you're a biologist or a physicist. And I think we have a lot of biologists and physicists writing about it, not as many chemists. And so it's sort of a disciplinary side for me. It's actually adapted from my physical chemistry class. I teach a physical chemistry survey. And through a number of of steps along the way. It actually grew out of some lectures for that class. And I also did a Weider lecture, it's like 6 years ago now. And so it grew out of that as well. And so it really is primarily from my perspective as a chemist, but it is also implicitly, I believe that, I believe that God created the universe, although I'm willing to figure out how he did it. And so it really is from my perspective as a Christian as well. And I try to integrate the two as I go through. I don't come right out, well, in a sense I do come right out and say that I am coming at this from a perspective of faith in the foreword, but I don't really come right out and say this is Christian science. That would mean something different if I just use those two words anyways. But it's not really Christian in its origin, but it's Christian in its interpretation. And it comes from a conviction that God did it and we're figuring out how. So that means it has a different perspective from a lot of other things. It's definitely not a six-day creation book. It's definitely a book that talks about how evolution worked to create the world around us. And so the idea is that God is creating through evolution. And if you're familiar at all with any of the faith and science discussions, this is not the default position for either scientists or for Christians. And so what I want to do with this book is I want to write from this perspective, and I just want to write naturally from this perspective and see what happens. So I'm not going to come out and I'm not going to assume that the reader has faith or even has that much in this term of chemistry background. What can I do telling a neutral sort of reader from my perspective how things look? Talking about science, talking about the evidence. And at the end of the day, we end up talking about faith in a certain way. We end up talking about philosophy. And it ends up being from a different perspective than from the common perspective that is there. But I intend for that to happen naturally. I'm not trying to impose this from the outside. I'm trying to have it grow from the inside. So the idea of what I'm talking about, the contrast is, there's really a contrast with my book from a famous book about natural history by Stephen Jay Gould, who's an incredible writer, a scientist that I hope I can emulate him in some small way in a couple of passages. I really like how he does things, but I think that he made he put himself out on a really far limb in one of his statements about how life works. And I would like to pull that back a little bit. For instance, this comes into most stark contrast when you look at his book called Wonderful Life, which is about the Burgess shale fossils. And I'm always saying this wrong. Is it Burgess? Is that okay? I just want to make sure I have to say this right, because when I talk about this, I mispronounce things all the time. So Burgess shale fossils, and Luke Reinsma actually mentioned this book. This is an incredibly well-written book. It was one of his top 10 books that he mentioned before he left. I'm not sure if any of you have been able to have a class with Professor Reinsma, but he recorded it and put it on YouTube, and so he's public about saying this. When he described this book, he said it was about the most disturbing sentence that I've ever read. It breaks my heart to read it, and I lost half of my faith reading this book. And the sentence in question is Stephen Jay Gould saying, we came this close, I can do this for you, thousands and thousands of times to erasure by veering down, by the veering of history down another sensible channel. Replay the tape 1,000,000 times from a Burgess beginning. This is the tape of life that he's talking about, the history of life. And I doubt that anything like Homo sapiens would ever evolve again. It is indeed a wonderful life. And he backs us up with a story that focuses on this one area, the Cambrian explosion, and the time when life first became complex. As I read it, I appreciate what he says, but I think it needs to be tempered by other perspectives, because my perspective differs from his. I would not say this. I would say something different. Looking at the same science, it's very important that I believe that all the science that Gould talks about is valid. In fact, I think that he doesn't give evolution enough credit, if you come down to it. And my perspective comes from the importance I see in chemistry and the perspective I take. I think that from a longer, wider perspective, you see things differently than Gould did. And so the whole point of the book is to sort of make this philosophical argument. If we replay the tape of life, what would happen? And of course, it's a huge question. It's not settled. But I want to offer a chemical perspective that would offer some evidence that might not be as contingent as Gould seemed to say. So, my focus in this talk is about how chemistry can pull complex things into order, and my thesis of the book is that chemistry pulled natural history into a sort of order on a very wide level. Enough clauses in that to modify it, right? Now, there are other topics in the book that you'll have to read it to find out. There's a lot about how art illustrates science. There's something about the three chemical shields that protect us, that protected the process. There's a whole chapter about origin of life chemistry. If you have questions about that, I hope to at least talk about the recent experiments that are why I think that life could have had a chemical origin. And a possible chemical cause for the Cambrian explosion. I do modify that with possible, but I think that there's some suspicious chemistry going on that I think may have caused that explosion of life that Gould talked about. And then at the end of the book, I get into some examples of convergent evolution. So this does come out to be about evolution in some ways. But that's only after complex life evolves, which is around chapter 8 or 9. So it takes a little while to get there. We have some other things to talk about first. So just an example of one of the things I don't have time to talk about, but is in the book. There's a chemical shield that protects the Earth. It's the ozone layer. And you can actually see it from a certain perspective. If you take the right perspective looking down on Earth, you can see this green visible emission that is from the oxygen that is in the ozone layer. And what it's doing is it's intercepting high energy dangerous radiation, and it's making it much safer for life. It's downgrading that radiation. And you can see it in that green color. It looks like something from Star Wars or something like this, but this is a real picture of what it actually looks like. So we do have an invisible shield protecting us. And as a chemist, I'm very interested in how that oxygen works. So it has that protective level. I want to take a different perspective, though. I want to take you down. This is down at the Earth level. You can see a sculpture by Roger Feldman. This is another SPU faculty member. I wanted to mention him because he teaches classes in art, so maybe some people have had him. He actually gave me my idea, by the way. He actually gave me the idea, sort of a permission, to do what I do in biochemistry too. You know, it's because he does what he does with students to build these things that I figured I could work with students to build proteins. And so I've been doing that for more than a decade now. So what he does is he builds these structures, and so this is his structure drawn by Gela, who is another art professor. And what you do is you walk into the structure and you look around. And to me, that's a metaphor for the scientist looking at the cell. We have this mysterious structure, and with science and experiments, we can actually walk inside it and look around. And in fact, it's like if you can think of the discovery of DNA as being like we walked into the cell and we found scraps of paper inside it. Okay, they are actually words. They are long polymers of chemicals from one perspective. From another perspective, they are words, and they even evolve like words evolve. So the idea is that we found these DNA words, and we can kind of project back and figure out where the cell came from. So this is all metaphorical, but again, if we walk inside, also we'll see something very constant across. Most cells have chemistry that will follow a pattern that we'll see again and again if we walk into and look around different cells. So if we walk into that cell and we're able to look around and see the levels that it has of manganese, of iron, of cobalt, of nickel, of copper and zinc. Copper will always be at very low levels if we're looking around at the dissolved copper in the cell. Zinc will be just a little bit higher, but still a very low concentration, very hard to see. And we'll see more of the other elements. Okay? Inside the cell, we see this pattern, and this pattern is more or less universal. It's more or less universal because this biological pattern comes from a chemical pattern of how these things dissolve in water and how they bind to other things. And so this is a pattern of the chemistry of how each of these elements binds to a claw made with two atoms of the listed elements up here. So this is like a nitrogen-sulfur claw, and at the bottom there's an oxygen-oxygen claw. The main thing is that all of these atoms just show a general pattern of stickiness. Doesn't matter if it's nitrogen, sulfur, oxygen, or what. The general pattern of stickiness is copper is extremely sticky to everything. Zinc and nickel are kind of sticky to everything. And as you go down, manganese and iron are not as sticky. This pattern mirrors and is upside down from the pattern of this, because the free concentrations of the cell, the resting free concentrations, come from, you have to have enough of the element around to stick to stuff, but you can't have too much or it will stick to everything and it will make it into a massive mess. It will make it into a cross-linked gel on the inside. And actually I pull a story from Dr. Ridgway's lab about how zinc will do this, and there's a paragraph or two in the book, so I cite you. There you go. So see, it's good to have friends at SPU because they give you stories that you can use in your book. Okay, so hopefully, and he can't take it back. It's public. I have to be able to use it now. Okay. So that's how chemistry and biology are related. There are some ways in which chemistry brings biology into order in that way. Now we can move across the fields, and if you see this, you can go to psychologists look at the sociologists and say sociology is just applied psychology. Well, then the biologists say psychology is applied biology, the chemists say biology is applied chemistry, and the physicists say, well, chemistry is applied physics. And then, of course, everyone forgets about the mathematician who's all the way over here on the scale of purity, she didn't even see the other ones. So as we go through the different perspectives of the different fields, we get different views of the world. I like how he has an octopus right there. But there's a way in which there's the rules of math make a pattern that chemistry must follow. And this pattern is seen if you follow this weird set of instructions, you'll get a very familiar chemical shape. Okay? Basically, if you start with numbers, and if you start with the odd, just count by odd numbers, 1, 3, 5, 7. And then follow this rule, double each box, and then slide the boxes around. And there's hidden in this math, there is a shape that you'll recognize. So we can count by boxes, 1, 3, 5, 7, double each box so we make a little pyramid. And then we slide them around so that we slide this, and this. And then we don't have room for this, right? So we're just going to slide this down. But then if we make this into a step scale and then we fill in all the steps beneath, then we get this pattern. This doesn't necessarily look familiar yet, but if I just do some arbitrary sliding around at this point and move this over here and that over there, oh, and that guy moves over too for historical reasons, I get something that looks very much like this. This is a periodic table of the elements, where instead of being pulled down here, this is inserted up there. You can build a periodic table from just counting numbers if you do it right. So I have a little gift for you all. Some of these are left over from this summer, so they're in color, but they also don't have the correct release date. And some of the other ones are, what I'll do is I'll mix these up so you can try to find a color one if you want. I'm going to start this one over here. And I will start this one from the back corner and just snake them around and they can meet in the middle. Okay? So everyone can have a periodic table. I know you've always wanted one. But this is actually a demonstration of another way to show how math shaped the periodic table. Because once you get yours, you can actually fold it in a way that each block gets folded away. Each of these 1, 3, 5, 7 blocks, which is actually a 2, 6, 10, 14 blocks. But that's because of the doubling rule. So you see that this block is 14 wide. This is our 7 block. So 7 elements right here. You can fold that down the middle and fold it away like you see up there. You can fold it back, and then you'll get the periodic table the way that you're used to seeing it. The way that we used to have it up on the wall until it was unceremoniously removed this summer, and we chemists are desperate to get our periodic table back. So hopefully in a couple of weeks we'll have the periodic table, and I can point to it. But for right now, I'll point to this one. This one can fold away. This is a group of 7, like that. Then you can fold the transition metals away. That's a group of 10. The block over here is a group of 6, 3 times 2, and that leaves a block of 1 times 2 over there. So what the periodic table does, and if you look at the numbers, by the way, you'll see that these actually do really fit in right here. This is the way the real periodic table should look, and we just rearrange it for convenience. Underlying the periodic table, there is a mathematical pattern, and that pattern actually comes from quantum mechanics, so Dr. Lindbergh or I in physical chemistry can teach you a little bit about why those integers are so important. And it has to do with why the orbitals have their different shapes. But the main thing is, as you look at that, you can at least, you can actually physically do it, and only the last one is really hard to do because it's so small. But you can see how that pattern comes out of it. So math helped build the periodic table. Math constrains chemistry. And you can't have any halfway elements. There's no such thing as an element 3.5. There's an element 3 and there's an element 4. You can't have 3.5. You can't have half a proton. Or if you do, then you're basically in an atom accelerator. You're not in chemical conditions. Okay? So there's constraints to what we can see, and life even uses fewer of these. If you look at the table, you see that only a few of the elements are colored, and each of those elements is colored by its general job in life, its biochemical job. You see that we have 3 jobs, and some elements can do 2 jobs, but you have elements that balance, elements that build, and elements that catalyze. Well, it looks a little arbitrary which one's which there, but it's actually not arbitrary. It's actually what determines what job an element does is its chemistry. One of the things that's important is how much of it dissolves in water. And so if you look at the elements and how much they dissolve, so here's the concentration of how elements dissolve in the ocean today. You'll see that the 7 elements, or 6 of the 7 that are used for balance, are very soluble. You have high amounts of them dissolved in the ocean. And those are used for balance jobs. The elements that are used for building jobs, they're in the middle range of solubilities. So they dissolve calcium, sulfur, and phosphorus are used for building, and they're all in the middle here, where the ones that are used for biochemistry are found at the very bottom. And the ones that you'll notice at the very bottom of this, we have like a chain. We have a chain of very soluble down to sparingly soluble, and these are basically insoluble. You have such low amounts that life cannot use them. Not enough dissolves in water. So what determines what life uses, which elements get the different colors on the table that I handed out, is partially the rules of solubility chemistry. The other thing is that these things have changed over time because this number, this O2, has changed over time, and the amount of oxygen around affects the solubilities of certain oxygen-sensitive elements. And so some of these have arrows. Like molybdenum today is high up, but it used to be low. Nickel used to be higher, but now it moved down. And copper today has moved up from being too scarce to use to where it was able to be used for biochemistry. And you can see the patterns of how all these changed by plotting them out, and you can even come up with chemical reasons for why the other ones that are listed are not used. And so I go through some of those chemical reasons. But the whole thing is that chemistry has sort of ordered the periodic table. It helps select which elements are used, and one of the main selectors is just, is there a lot of it that dissolves in the water? So I have I wanted to do a demo because I'm a chemist. We have to do demos. And I wanted to turn a mixture into ordered layers, and so I have 2 versions of this demo right here. If I turn on the document camera. Okay, so what I have here, this is the version that I can make from the, it's a little bit hard to see. If I hold it down here, you can sort of see the 3 colors. There's 3 liquids, and there's some salt at the very bottom here. So there's 3 liquid layers and 1 solid layer. And this is what you can make with just stuff that you can buy at a drugstore once you get off a plane. Because you can make another one right here. This one has 4 layers. It's a little bit hard to see. I'm going to pull out another one. This one, you can make a 4-layer thing. So this is like the salad dressing, oil and water separating. But you actually have 4 things separating from each other rather than just 2. And here you have 3. This just includes some flammable stuff that I don't want to have to explain to the TSA. So you can see this version, but if I have to get on a plane to show someone this stuff, they're getting the other version. I can take salad oil on a plane. I can say that that's not flammable. I don't know if I can take this, there's silicone oil and there's, benzyl acetate or something like that. Yeah, I don't want to have to say that. The fact of the matter is the oil is probably the most dangerous thing in there, but I don't want to have to explain it. So you have here, you can see that there's 4 layers. Now what I can do is let's take this one with the 4 layers, and then let's also take this one with the 3 layers. And you see that if I just mix them up, okay, we have a bunch of brown layers. They start to separate immediately. You can see that some of the oil and water are separating out here, and some of it's happening here. So I can perturb the system, but then it will return. The chemistry will reorder it. It will bring things back into order. Now, however, it's not complete yet, and this one's still just 2 colors. You know, it's just starting to get a few bubbles there. So if I want to speed it up a little bit, I use my chemical apparatus here, which is a modified salad spinner. Salad spinners are just centrifuges. And so it's not perfectly balanced, but actually it works pretty well. It's hard to show because I didn't realize I have to tilt that to show it. But you can see here's the 4 layers again. There's a yellow layer in the middle, and this one you can see the 3 layers reformed. And so I was able to speed up what would happen naturally by applying gravity, applying a force, a physical force, or acceleration. It's not really gravity, but gravity is acceleration, so I think that works. So I had some fun playing around with that and trying different mixtures. There actually, if I could use mercury, I could do 6, okay? But I don't want to use liquid mercury, so I can just tell you about that, and we'll leave you to imagine it. So that's a case where chemistry, I can disorder the system, but chemistry pulls it back into a certain order. The same molecules, the same atoms are not in the same place, but the system is still in a definite order. Okay, so you can do this with these materials that you can even find in downtown Grand Rapids, Michigan, which for some reason doesn't even have drugstores. I actually got my stuff from the hotel lobby store because I couldn't find a drugstore within walking distance. So I was able to put that together that way. So this happens in a biological way as well. If you have a combined biochemical system, you can also see separation into layers. And this is a neat experiment you can do. If you take a bottle of mud, basically, and seal it up, you give it a carbon source, you shake it up, and the most important thing, seal it up and leave it out. Leave it out where the sun can get to it, because the sunlight will drive a separation. If you come back later, you will see different layers of bacteria that form. The bacteria on top will be the ones that metabolize more oxygen. The bacteria on the bottom will be the ones that don't, and they will metabolize more sulfur instead. But you see there's a chemical order to these because the oxygen-loving ones will be on the top, especially the photosynthesizing ones that will take the sunlight and be producing oxygen that the other ones can eat. And then down at the bottom you can have the ones that are trying to get away from oxygen. But just that pattern, the pattern driven by oxygen, driving things to be at the top and bottom, can make these incredible layers of these different kinds of bacteria doing these different kinds of biochemistry. This is an example. It's called a Winogradsky column, and you can actually order them online from the Hiram Genomics store if you're curious, or you can make your own, and you can see that you can get various layers. And you can make it, basically, it makes a rainbow. It's microbial action making a rainbow for you. The ones at the bottom will tend to have very different biochemistries. I pointed out how they had a lot of sulfur down there. There's also methane down there. Stuff that's flammable if you expose it to oxygen. So it's chemically incompatible with oxygen as you go down in the Winogradsky column layers, and also as you go down in layers of mud at the bottom of a stagnant lake. As you go down, you get less oxygen, and you get more of these non-oxygen chemicals, to say the least. And again, if you bring the two together, so if you can bring some of the the methane that these sediments are producing up to the top, you can light it on fire. And so this is called the Volta experiment that, that shows that these are storing energy. When you bring them in contact with oxygen, you can release that energy in an explosive way. And so these are reactive with oxygen, and they're also, they live in a place where oxygen is not. They're anaerobic. So if oxygen changed over history, over billions of years since life started, oxygen changed. And so if you have very different chemistry when oxygen is around versus when oxygen is not, and very different elements when oxygen is around versus when oxygen is not, then you could possibly have the chemistry of oxygen pulling history into ordered layers, in a sense, over time. So look at this. This is age billions of years ago. So life started around here. And at that time, oxygen was really low. This line right here is oxygen. Photosynthesis was invented. Oxygen started to be produced, and it filled the atmosphere. The exact shape of this line is a whole story that takes the book for me to completely explain why it did. But for the main thing I want to say is there's no oxygen, then there's a little oxygen, then there's a lot of oxygen. And there's 3 layers. So the first photosynthesis happened right before oxygen came up to its middling sort of layers. And then there's, right after oxygen jumped, you start to get complex fossils. And so the hypothesis of the book is that the chemical event is connected to the biological one. And that you have these 3 layers of time. You have different kinds of organisms in each of these layers of time, and different kinds of biology, and different kinds of chemistry. The BIFs are different kinds of geology, because the BIFs are kinds of geological formations that form when iron reacts with oxygen. And you can see that they happen, they appear to be centered around these leaps up in oxygen. So the idea is that the whole Earth changed. All the disciplines, everyone standing on that comic that we had, from math to sociology, would be able to observe some kind of change that happened as the Earth went from early Earth to the present day. And so this is a more ordered view of history than a random free-for-all. This can be connected directly to biology. Notice that this is a scale that we've zoomed in. Now we're down to the positively recent times of 600 million years before present. But it is a very different, we're far on the right end of that graph. And if you zoom in and you talk about where how the oxygen went up, oxygen and life both increased and decreased in a possibly connected pattern. Okay? The idea is that oxygen increased before life had its big increase. And so this oxygen increase precedes Gould's Burgess shale observations. I think that it's possible that we could have causation on top of correlation in this case, because there's a chemical reason why that extra oxygen could have helped that happen. That's chapter 9, okay? So I have it right there, but I can't let any of you read it until it comes out. So that makes you want to read it, right? Okay. But as oxygen changed the world and it changed the chemistry of the oceans, the things that were sensitive to oxygen changed as well. And if you arrange things according to their sensitivity to oxygen, and you consider that we start, when we have low oxygen, we're on this end of the redox scale. So we can arrange things by their sensitivity to oxygen, and we can say that things on this end of the redox scale, as oxygen increases, we're sort of increasing along this scale, okay? And we're sort of flipping, as oxygen increases and the Earth is oxidized, then we're flipping from the predominant form on the left side of the scale to a predominant form on the right side of the scale. The main thing I want to point out here is iron and copper. Notice that iron changes as the Earth oxidizes. The iron oxidizes as well. It goes from iron 2 to iron 3. The copper oxidizes, which means it goes from copper 1 to copper 2. But the key point to this is that iron 2 is more useful for life. Iron 3 is less available for life. And so iron becomes less available. Copper 2 here is actually more useful for life, and copper 1 is less useful. So this would predict from chemistry that we would see a pattern that iron would be used less and would be harder to use as life went on, and copper would be used more. In fact, you could even sort of, in your mind, superimpose an arrow on the periodic table where life moves from an iron-cobalt using realm, iron, cobalt, and nickel, in fact, towards a copper and zinc using time. And so these would be associated with the different colors that we had on the previous slide. Like these would be associated with the low oxygen colors, and these would be associated with the high oxygen colors. And there's many ways in which that fits and that works. Copper is used more for complex animals, and it's used on the outside of the cell in certain ways. So this is a way, an idea that chemistry pulled biology into order, and if this works, then there should be ways in which chemistry pulled history into order. And so here's one small way in which it might have happened. It's a similar graph to the other one. Okay, so you see that we still have redox potential, oxygen sensitivity at the bottom here. But you also have, if you arrange them by redox potential, and actually if you reverse the scale, because now you're not talking about things that dissolve in water. You're talking about how easy it is for humans to dig down and remove these things from the earth, which is actually sort of the opposite. And so if you flip the scale around and you just put the metals that are useful to humans on the scale, then you see an interesting time-based pattern. Not an absolute pattern, but definitely a tendency, because gold, silver, and mercury and copper, they are all very old. They've been used for a long time by humans. And here's the time when they were first used. And you can see that mercury is a relative newcomer, but all of the things at the bottom are BC dates. Now, it's not an absolute pattern. You have an iron as a BC date up here, but excepting for that, if you look up and down, everything on the top of the scale, everything with a negative redox potential, according to this scale, is in the 1700s, 1800s, AD. And so you have the idea that the reactivity of the metals might have determined which ones the ancients used most. So reactivity and abundance work together to make these be the metals that were in the, each of them is assigned to a planet. You know, each of them in Greek thought is assigned to a different god and a planet, and they knew how to use it. So chemistry started at the bottom of this graph and then gradually moved forward until we got to magnesium and aluminum. You might not think of it this way, but aluminum is actually a very modern metal. So the idea is that chemistry is a layer, is even a discipline. As a discipline, chemistry offers a perspective and pulls these different things into a sort of order at certain levels. This doesn't mean that chemistry determines everything that happens. I'm just highlighting the ways in which chemistry provided a kind of order that is specifically chemical to these very different ways of looking at the world. The idea is that the chemistry layer of life made the biology layer more predictable. And my thesis is that it must be predictable because this sequence was predicted by R.J.P. Williams in the 90s. In the 1990s, R.J.P. Williams said, I think that life followed this chemical sequence. And this was not confirmed until the genetic analysis came out in the past decade. So starting around 2005, 2006, we got to look at the genes, and we saw that yes, indeed, they do follow this pattern, especially with copper genes, for example. You only see copper genes in recent genes. In the oldest genes, you don't see copper using genes. And in many ways, the same patterns that I talked about can be confirmed by genetic analysis. Again, it's in the book. Okay? So that means that chemistry set a sequence for what could be used by life when. And so that means there are many paths that life could have taken, but it looks like life could have taken if you don't consider the chemistry. And then you would say that the narrative of chemical ability actually constrained the paths that life could take. One of the main examples is DNA is made of phosphorus, not arsenic, for good chemical reasons. And when somebody proposed that they found DNA made of arsenic, after a year and a half, that was found to be not true. Even the most extreme organism did not make DNA out of arsenic. So each of these chemicals has a specific job. And this makes Gould's quote look a little bit different. It doesn't really say much about exactly the Burgess shale interpretation, but it takes a wider view, and it says if the tape of life was replayed, certain chemical aspects would repeat. So it wouldn't be a completely, I don't think we can say that we came this close to being not here. Okay? I think the chemistry gave a certain order as oxygen increased over time. So Gould has this idea of extreme contingency, and I say that contingency may even exist on the biological, morphological level. Shapes of species may differ, but biochemistry would repeat. And in fact, the Origin of Life chemistry chapter is important to this, because if we can ever come up with an experiment that repeats Origin of Life chemistry, we are replaying that part of the tape of life. So you realize if you don't like the idea of recreating life in Origin of Life chemistry, it actually does have a good part to it. And I think it's a part that makes the universe look a little more ordered if we can repeat it. I really don't know, but I talk about the reasons why there might be ways to think about it that way. And really this comes down to philosophical questions. So if you want to talk about is creation ordered or is it disordered? Is it determined or contingent? Is there fate or free will? And I want to say that faith does not really answer these questions. In fact, faith doesn't even, I think faith has a place for looking at the world that sees both a randomness and a constraint to that randomness. So that's why I don't want to say Gould is wrong, but I want to say that the interpretation is too specific. The interpretation of history is wrong, really. I guess I'll have to say that for something, you know. So there's one chemical example I want to leave you with because you guys can handle this. Because this is some chemistry that just came out. What looks random at one level may turn out to be law-like at another. So it's this paper right here. What this paper is about is it's about the process by which oil and water separate, just like this. When this happens, you see little globs of oil floating around, and then they join together, and then they become a big layer of oil, right? And so the process by which they separate is called coarsening. And originally, all the chemists thought that it was driven by just randomness, just random Brownian motion. Now, it moves because of randomness, but the question is it really driven by entirely random collisions? If you look at how fast it happens, it actually happens too fast. It happens faster than a completely random collision model would expect. So this paper talks about how they propose that there is a dynamic property of water as it moves around, that the oil droplets don't just move around randomly like they do in this picture right here. They say that doesn't happen. They say rather the oil droplets move as if they are attracted to each other. And the reason is a very complex dynamic form of chemistry involving flow fields, but the whole thing is it's modeled in a computer that's following complex physical laws. So in this case, physics is constraining the chemistry and causing this to happen faster than it would otherwise and giving order to the randomness. Brownian motion is still existing, but it is constrained and hemmed in by this law so that things happen faster than they would if they were completely undirected. And so that's chemistry for you. And they had this. In other words, a larger droplet tends to eat a neighboring smaller droplet by direct collision. And I really have to admire somebody who in nature communications uses eat as a verb, because I think that makes it clear what's going on. So the end is that I believe that we need both perspectives, both Gould's perspective and the perspective that I wrote in this book. Biology and Gould give a close perspective. Chemistry gives a more distant perspective. They're looking at the same thing. We had the sky up there, it says Huckleberry Finn, all speckled with stars, used to lay up on our backs and look up at them and discuss about whether they was made or just happened. And this is Binkley and Oliver. Oliver is the rational scientist. Binkley is sort of the starry-eyed dreamer. Binkley says made, Oliver says just happened. But at least they're in conversation, you know, and they have things to say to each other. And so that is what my book is about. I wanted to leave, I've got about 5 minutes for questions. But I do want to say, they gave me a promo code, so they said give this to your friends and colleagues. So since you guys are colleagues, if you think you know someone who might be interested in this book. It doesn't come out till March, and it's a great Easter gift. But I do have a promo code that you could actually enter in, and you are welcome to use that. They haven't told me yet that I couldn't give it out to students, so there you go. And just a hint, if you're taking my physical chemistry class, we will be using this book this year. So it's one of the perks of writing a book. You can assign it. But it will be cheaper than a textbook. That's a good thing. Okay. There is one on, this is actually from the Oxford University Press website, so that's where you can get the discount. Amazon, it's already up on Amazon, and you can pre-order it and like push it up, but you don't get the discount there the same way, I don't believe. Okay, so we have 3 minutes left. I would like to know, what questions do you have? I had to sort of run through that, but I wanted to give you guys some of the science. What questions come up about any of that? Liberal arts, science, or whatever? Process of publishing.
I was wondering, when looking at the periodic table,
Yeah.
that you suppose that while the first column has 1, and then you said it's 1, 3, 5, 7, right?
Right.
But did you say why there would be like 2, 3?
Yeah, the reason is there is a fundamental rule for electrons called the Pauli exclusion principle. But the basic thing is that the electrons can pair up if they have opposite spins. So 2 electrons with opposite spins, and what is spin? It's not really technically spinning around, right? If you talk to a physicist, you can't pin them down. But it's a basic way that electrons work, and that's why you multiply by 2. Each orbital can hold an upspin and a downspin electron. But yeah, I wish it wasn't that way because it would make it simpler, but quantum mechanics, yeah.
Out of curiosity, I'm mixing a lot of fields. So writing this book, from which field do you see criticism?
That's really an interesting question. So like, where do I see criticism coming from? There are a lot of people these days. It's actually kind of fashionable to be taking pot shots at Gould right now. So I'm a little bit concerned about saying that such a brilliant guy was wrong. But I actually feel a little bit more comfortable because he did put himself so far out on a limb with his statements about the tape of life that I found like dozens of papers that specifically refer to that and specifically say, we don't see that in this case. And so, but I do think that there are some people that will be like, oh, you're attacking Gould, you must be against evolution. And they might attack me for that. And then, of course, the people who don't like that I have an uncle who doesn't like that I believe in evolution. And you don't really have time to sit down with these people and give it the whole explanation. But I'm very curious how he will respond to reading my book. He's liked it on Facebook for what that's worth. And they have evolution as like the 6th word in it. I'm like, okay, yeah. So I'm trying to do this as a conversation, and I hope it will be taken that way. But I also know that it's a very polarized atmosphere, and what I'm asking for is not something that typically happens. So it's kind of an experiment. We'll see. And it's one of the things I want to talk about as we go through the classes and read that. So I hope to address those things as we go through. All right. Thanks, everyone.
Thank you very much.